Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Holograms sitting here.
Save the application state.
Ah, yeah. We are in heat.
Just be able to do that.
4. Yes, except it's not all, it's 4 for some reason. Let's do that 4 something. I thought it would have been better if it would have been, but anyway, that's what it is.
Okay, thank you very much for coming. We have a busy time, and today we have Timo Roos from the Helsinki Institute for Information Technology here, and he's going to talk about some work on localization, not based on GPS, but based on multiple wireless sources, very suitable for indoor, if I understand correctly, and mobile devices.
Thank you, Thure. Yes, so Thure asked me to talk on this, and actually we have been just doing some recent work. So this is the work that I'm presenting is, at least the latter part will be unpublished work. So don't tell anyone, right? Okay, so these location-aware services are, of course, useful, and there are many reasons why they are so. Emergency calls, we would like to know where people are when they're in need of help, earthquakes, for instance. While I was coming here, of course, I had a little bit trouble finding the right building, and I would have liked to have a system that tells me where to go and whether I'm in the right place or not. And of course, for entertainment, there are different types of games and scenarios where you would like to know, for instance, where your friends are, or people that sort of potentially could be your friends are, and various services are already being used, of course, based mostly on GPS. But oftentimes we're indoors, like now, and many of the systems start working less well when you assume that GPS signals are being received with good coverage. And this is due to the, of course, due to the buildings blocking the signals and then causing also reflections and all sorts of other complex signal propagation scenarios where the sort of mistakes will be high. And in contrast, actually, often if you're trying to look for an office, for instance, or a coffee machine, or a toilet, you would like to know very precisely where you are, and not only with like a couple of dozen meters accuracy. So we would need something better than just GPS, as it is for indoor use. And of course, there are various methods. GPS, if it works, will give you something like 10 to 1 meter accuracy. I suppose it's somewhere here. Then there are systems, special system, sort of tailored systems that give you 1 millimeter or even higher precision that you use for scientific measurements. But those have to be installed somewhere in a lab sometimes. And all kinds of systems that are basically based on technology and features that you have to specifically install to the place where you're going to use them. But there's also, and this is what I'm going to talk about, systems based on Wi-Fi or wireless LAN networks. Since they are also based on similar communication based on radio waves, they can be used for positioning. So here's, just to give an example of something that is not based on that, before we go to the wireless LAN network thing, I just bumped into this system that I find is very nice idea, that you put in your foot an accelerometer, so it measures how fast your foot is moving and to which direction. And once you enter a building, you lose the GPS coverage, then it starts to sort of figure out where you're going based on how your foot is moving. The problem with that is you sort of gradually lose track of where you are, because the small mistakes, they accumulate. But there's this system called FootSlam, I think it's called, where it builds a map while you're doing that. And if you go around a few times, it will realize that you're always returning to the same place, so you're walking on the same corridor, for instance. But anyway, this is what I'm really going to talk about, this wireless LAN positioning. And it's based on the fact that the received signal strength depends on where you are. And of course, then if you observe the signal strength, you can sort of infer backwards your location. And this is being used in various ways. There's a company called Skyhook in the US that does this basically based on which network is accessible. So they have a, yes?
I was going to ask, what was the problem with the previous slide? You just showed the slide. I didn't know what was on the y-axis, but on the x-axis, it seems like pretty much everything is covered. So what's wrong with this?
Well, I will get back to that, but we're basically happy with the fact that, I think, yeah, that's a good question. What is on the y-axis? This is something I don't actually know, but we're happy with this precision usually with the wireless LAN positioning. But this talk is going to be about improving that and getting that sort of more easily available, because it requires certain sort of tasks to be performed before you can use it, and we're going to make those tasks easier. So this is basically where we're going to end and not go anywhere in this graph. Thanks. So this wireless LAN positioning at this coarsest mode is just based on the fact that you sometimes hear or sort of can access a network, sometimes not. And of course, since the signal strength tends to be lower when you're further away from the from the base station. Trying to look, there's one on the wall. So if I go further away from that thing, then the signal will be weaker generally. And then I could basically try to estimate the distance and do some sort of triangulation. But the problem with that is that it's not very regular, the way it diminishes. If I go that way, it probably goes pretty slowly down. But if I go that way, because there's a thick wall there, it will get it will sort of decrease more sharply, and the distance estimation will be difficult. To improve on this, we can build these radio maps. And the radio map essentially predicts, given your location, what the signal strength will be. And so, assuming that the base station will be somewhere here, then the green and the yellow colors show areas where the signal is stronger. And after a wall, you can see that it becomes red pretty fast. So after a wall, you easily lose most of the signal strength. And in order to sort of figure it out how it goes, you can build a propagation model that says, well, a wall diminishes the signal by such amount, and just count how many walls there are in between or something like that. Or you can even use some ray tracing methods that take into account the fact that the rays can actually bounce off walls or other obstacles. But you can also, and this is what I'm sort of most interested in, you can think of this as a machine learning problem. So the location is the label you're trying to infer, and the signal strength of not only one but several base stations, several channels, are the inputs or the features. Or and then we can think that, okay, we'll train the system by showing it, okay, here's a location and here's how the signals are here, and here's another location, and we measure the signals again, and the system will be able to learn that mapping. And here's an example of how people sort of are using this Ekaho. It's a Finnish company that is sort of I used to be involved with to some extent. Now I'm just downloading their pictures and stealing them in my presentations mostly. But they have this product called Site Survey, and it has a free version called Heat Mapper that you can install, and you just have to put the floor plan of your lab, and then you can walk around and tell it, okay, now I'm here, and you can walk a little bit further and say, now I'm here, and it records those signal strengths. And what it does is interpolates and extrapolates the measured signal strengths, and it gives you all over the network the coverage, and it can also to say, okay, here you can access the network, and here the bit rate or the error rate will be higher or lower. And you can use that for planning the network, for instance. If you're wondering, in the lab the network is usually bad, you can sort of try to infer why, and then just throw in a couple more base stations, or something like that. But the problem with such learning scenario is that, like the dimensionality, well, I wouldn't say P is greater than 10. The number of base stations, channels is high dimensional yet, but still it's high enough to be somewhat of a problem. And also the fact that the signal to noise ratio is very high. By that I mean that the change in the average signal strength over, say, 10 meters might be smaller than the standard deviation of the variance just due to or the variation due to just random fluctuations in the signal. So it's not very easy to determine where you are. Yes.
So when I look at my device and it shows me a list of networks available, is that truncated in certain signal strength? Are there really some more hidden signals that it wouldn't show me because they're not good enough for data transfer, but that you could still use to help the localization problem?
That I don't know. I think it depends on the system that is showing you the list. But of course, like in principle, all the networks in the world, their signal is non-zero here. But it's just the system cannot possibly sort of infer which network is there. But yeah, so usually I should have taken a sort of a system to show the networks. But here probably you can hear much more or access much more networks than you will be ever using to transfer any data. And sort of the good thing about this reminds me of the good thing about this is that you don't have to have access to the network to measure the signal strength. So you can get the idea of the network, and you can get the signal strength, even if you don't have even if it's a closed network, you don't have the password or anything like that. So you can use other people's networks for this as well. So the problems were that there's potentially a couple of dozen different variables or features, being the different channels in the network, or the different base stations, and that the very sort of variability just due to randomness or just whatever is going on around you, people moving, closing doors, opening doors, that's high compared to the changes in the signal strength, typically. And this means basically that we need a lot of data to train these systems. And this is made difficult because it's a lot of work to walk around and tell the system where you are every time. Of course, if we have GPS coverage somewhere, we can sort of record this place labeled, location labeled instances very easily, but then of course we don't need such systems anyway if we have the GPS. So I've been sort of doing this a few times, indoors and outdoors, and it's very tedious to walk around and then point on the map, now I'm here, and then again walk, and then point, I'm here. That takes a lot of time and effort. And this is basically the problem we're trying to tackle here. And the idea that we have is based on semi-supervised learning. So you would label only some of the instances. So it's based on the fact that if you assume that the location signal strength dependency is somewhat smooth, so that it doesn't really go abruptly up and down all the time. And we assume that the map is we can assume it's a 2D area that you're trying to map. Then this means that the signals the data in the signal space is also lies on a 2D manifold. So it could be wrinkled and could be curved in the signal space. But since we assume that the dependency is somewhat smooth, it should also, the topology of your map should be retained. So if it's a rectangular area you're mapping, you're gathering all the signal strength while moving around, then the signal strength in the signal space will also look a little bit the same, but it's going to be curved in the space. I'm going to go show some examples later.
Hey,
yes.
First of all, are you assuming that somebody has labeled the location of the station?
No, we don't use that information at all.
So are you assuming that you can get an accurate map of the building?
Well, not quite. We're just using where we have access to some of the signal strength measurements. So these are vectors showing for each base station it has sometimes accessed. What's the signal strength at any given moment?
Yeah, I'm not quite understanding what your model is. You're assuming this software is installed on one laptop, and that one user is just meandering around their building, and you're not being provided any map of the building or any idea of where in the building the stations are? Or you're assuming that you're correlating data across multiple users, or you're assuming that you do know how many base stations and where they are, or assuming you have a map of the building but you don't know what base stations are in it? Or I just am trying to understand more what you're assuming that your scenario is for this.
I think you basically don't have to know anything except the data. Then, of course, in order to map, we will later map the the manifold from the signal space back to the geographical coordinates. And for that purpose, we need at least some labeled instances. And by labeled instances, I mean instances for which the geographical coordinates are given. And then, if you want to display your position on a map, of course, then you need the map, and you need to relate that map to the geographical coordinates. So basically, the scenario would be that you give me a map of Microsoft Research Lab, and then I have this laptop. I just walk around for a while, and for some of the instances, I will point where I am at any given moment, and for most of them, I will not. And then that should be enough.
And the 2D, 3D thing as well.
Well, so if I go to different floors,
right,
then it will be
frequently, of course, you do actually see base stations that are on the floor.
Yes, but that's not a problem at all. I mean, it will not sort of care at all. The problem is that the practical problem is that sometimes you don't. The signal strength is so low that you can't even measure how low it is. You cannot associate the signal to the base station, and that causes missing data in the signal strength variable. And that's a practical problem. But we just sort of what we deal with that problem is we just set them to a very low value and assume that's the value observed. So we'll essentially truncate the values from below. Okay.
Take those first.
Yeah, so just a question about this location RSS dependency smooth assumption. Are you assuming a static map of the RSS across the 2D manifold? So, or are you sort of relearning those things continuously?
Yeah, for the moment, and what I'm talking about now, I'm assuming it's static and it doesn't change over time. But of course it will, and that will sort of degrade the performance of the system. If some, like for instance, people move around, as I said, people move, open doors, close doors, that will change somehow the dependency of the signal strengths on the location. And then in principle you should recalibrate the system occasionally. But we've tried it like with an interval of a few weeks, and it didn't really significantly change at our department where we did it. But yes, that's a sort of good point. We would somehow have to take into account the time variability of the signals.
Just worrying about any assumptions on channel coherence time. You're saying that your measurements are showing that over weeks you're getting fairly stable RSS.
Yes. There was another question? Yes?
Two questions. One is the why aren't you making use of where the base stations are? I mean, I thought, like, for example, related work like radar, that's what they did, right? The triangulation stuff.
Well, I think radar is based on not triangulation, but just nearest neighbor matching. So they collect a database of all the instances are labeled by the location, and then the next one, the unlabeled ones, are mapped to the nearest one in the single space. So they're just using nearest neighbor. And they're not using the locations of the base stations either. But that could be used somehow, I'm sure. It could somehow provide, especially, for instance, if all the locations are unlabeled, then you could, for instance, find the one with the strongest signal for any given base station and assume this must be the location of that base station. And then if you knew, so, or vice versa, this vector must have been collected at the location of that base station, and you could sort of somehow get automatically labeled instances. So somehow that could be used, but we're not using it anyhow.
And second, like, minor thing, have you thought, like, for example, if I want to do this in this building, I could easily make use of, well, easily, I don't know, I have to talk to security, but every room or in every corridor, there's a little camera up there, right? And just as I'm walking around, I could arguably get some labels from them without needing to enter anything in the map.
Right. That's another good idea. I mean, we could get the labels by not pointing on the map ourselves intentionally, but we could somehow try to deduce them from other sources. Of course, as I said, GPS if it's available, but the cameras could be used as well for that purpose. Yeah, and yeah, various different things you could do. Anyway, so we're now assuming that the dependency is somehow smooth, and that implies, as I said, that the manifold on which the single observations live in this single space is somehow a curved version of the area in which you're gathering the data. Okay, so what we'll use is sort of apply this idea, sort of exploit this idea and apply a well-known method for manifold learning called PriceonMap. It's very, very simple to do that. And here's the usual Swiss roll example that everyone uses to demonstrate this idea. So now this is a 3D space, and there's a 2D manifold curved inside this 3D space. And the task is to somehow infer the structure of this manifold. And what PriceonMap does is it builds a neighborhood graph. I will explain later what it is. And by that exploiting the properties of this graph, it somehow tries to estimate so-called geodesic distances between points. So not points in the Euclidean space, but points along the manifold. And then do multi-dimensional scaling on that. So reduce the dimension of the high-dimensional space, exploiting these distances. Okay, so here's an example. I did last night, and as I said to Ture, I was in this nice pub before that, so somehow it looks like was a nice pub, yes. So here we go. We have these points here on the screen, and these red lines are now the neighborhood graph. And the neighborhood graph gives for each point, in this case, the two nearest neighbors in the Euclidean space. So okay, let's go back one step. So here, the point here is connected to its two nearest neighbors. And we do that for every point in the graph, and so we get this neighborhood graph. Okay? And now we just, for illustration, we pick 2 points, and I will define what is the geodesic distance, or what is the distance used in the PriceonMap algorithm. So of course the Euclidean distance is this gray thing here, and it is short for these 2 particular points. But the PriceonMap distance, or the distance that the PriceonMap sort of considers is the interesting one, is the shortest distance along the neighborhood graph. So you pick the shortest distance connecting the 2 points in the graph, and you just take a sum of the edge lengths. And the edge lengths are the Euclidean distance between the neighboring points. Okay. So this kind of makes sense that since we assume that the structure of the data here is somewhat of a linear, or non-linear, but one-dimensional structure. It's like a snake or something. And these 2 points are almost at the opposite ends of the snake. So it makes, in that sense that that the blue distance is larger than the gray one, right? And here's another example with the Swiss roll. So here, 2 points here, they're close in the Euclidean distance, but the geodesic distance along the manifold is much larger. And when you do the neighborhood graph, it will indeed do this. So the red line is now the distance when you're sort of traveling on the neighborhood graph. And then once you stretch it out, the roll, then it looks like this. This is again the true geodesic distance we would like to get from the data. But since we have a finite amount of data, it will actually do a little bit of wiggling, but still it will get you something similar to the actual true distance, as it were. And this is really, I just did this 2 days ago to do the simulations, and it's really this simple, assuming that you have multidimensional scaling as a subroutine. So this is how it works in R, and that's really all the code. So it starts here. We get the data. This is not high-dimensional vectors. And we want to get the neighborhood graph. So we call this function. And this is probably very, very bad R because there's a loop. So anyone who knows how to do this better, I would like to know because I'm really bad at R. Anyways, what this loop here does, it just puts all the distances that are greater than the, say, 2 or 3 shortest ones to infinite. So if you have all the possible distances from one point to the other point, you pick 2 or 3 of the shortest ones, depending on what the value of k is, retain them, all the long ones you put to infinity. So essentially the neighborhood graph will be sparse. So there are no edges between points that are not near or nearest. Okay. And then it says that this is the adjacency matrix. And this adjacency matrix will be used to, well, this is just saying that it will be a weighted adjacency matrix. And that essentially gives you the neighborhood graph. So as I said, we'll use it here, and here you'll just compute the shortest paths along any 2 points using this neighborhood graph. And then you do multidimensional scaling on that. And I will not go into the details and explain what multidimensional scaling is, but it's just a simple method to try to find a low-dimensional representation, in this case usually 2 or 3-dimensional representation of the data, where the distances are retained. The distances that you give to it are retained. So we want to find, say, a 2-dimensional embedding of the data in 2-dimensional Euclidean space, where the distances are as close as possible to the shortest paths on the geodesic distances. So I'll show how it works. And this is actual data from, I hope you can see it, but this is actually data that we collected for the experiments. So these are now single strengths. Every red ball is one single strength vector. I've sort of projected it down to 3 dimensions here using the original Euclidean distances. So this is essentially PCA. This is what the data looks like. I couldn't show you the I don't know, 15-dimensional data set, but I can show you the PCA projection of that 15-dimensional data set.
But what are the 15 dimensions?
Those are the base stations, the different base stations. So this is what happens if you just look at the data as it is. So it's not very separable. This is supposed to, well, you will see the structure of the map that was used for generating the data, but you can't really see any map structure from this picture. But the next, I will show an animation where this is gradually moved to the ISOMAP projection to 3 dimensions. I will use 3 because it will sort of better show how the map looks, how it's still curved. But so this is PCA. This is essentially doing multidimensional scaling on the Euclidean distances in the plane signal space. And then I'm starting to sort of add to this. I'm taking a convex combination of the Euclidean distances and the shortest paths on the neighborhood graph. So in the other extreme, this is going to be ISOMAP, and in this extreme is PCA. So I'm going to sort of gradually move from PCA to ISOMAP. Okay, so let's see. Okay, it starts. Great. And I'm already sort of, at the same time, I'm turning it a little bit to see better how it looks. And already from this one, you can basically tell what the structure was of the area that I used to collect the data. There's a big room where you couldn't enter in the middle, and there's another one here, and it's a long rectangle this way, and in the middle there's a corridor between them. So it looks like the digits 8 in a way. There's two rectangles next to each other and a corridor in between. I will show the map later. So
when you're calculating distances in the 15th dimension, what are you using as your norm?
it's the Euclidean norm. So now now the distances are sort of completely determined by the shortest path on the neighborhood graph, and now I'm sort of, just to repeat, let's look this at the animation backwards, going back to PCA where there are the Euclidean norms. So go back again, and you can see that the points, they start spreading around and being sort of convolved with each other, much worse. Right. Okay. So to summarize, what we do is we reduce the dimensionality of the data to 2 or 3, and once we've done that, we can already see how the map basically looks like. How was the area where we gathered all the data? But we still need to map this somehow to the geographical or your floor plan. Otherwise, this is just like arbitrary. You could rotate it and it doesn't change. The ISOMAP has no idea how to relate this to actual geographical coordinates. But this is now much easier than it was in the beginning, because now the data is 2 to 3 dimensional. We can easily learn such mappings from a few labeled instances in the data. Okay, so here's the data that I showed again, and now we've added something like 40 points that are tagged by their position. Previous ones weren't, and then we can learn a simple mapping from this space. This is now the manifold coordinate system to the actual geographical coordinate system. And we're doing this basically by linear regression, but we throw in the squares of the manifold coordinates so that we can actually allow some sort of distortion here. And you could use some sort of nonlinear regression if you want to do it even more flexibly in a way, but we've seen that this seems to work fine, and it requires really only a couple of points that are labeled. And I'm just showing that what we do, just to say again what we do, these are the geographical coordinates. This G sub I of superscript x would be the x coordinate of the ith labeled point, and we want to match it as well as possible to the manifold coordinates and their squares. And we just estimate this beta hat x to map that, and then we do the same for the y coordinate and minimize that. And what this is useful for not only mapping the manifold onto the geographical coordinate system, but this is useful also because there's in ISOMAP there's this one crucial parameter, that's the neighborhood size. So in the example that I did, I always connected to the 2 nearest neighbors, but I could connect to 3 or 4 or 5 or so forth. And this is very crucial because sometimes if it's very sparse, it will sort of be sensitive to the randomness. Sometimes it doesn't work so well. Some points just happen to be further away from the neighbors than the others. And in the worst case, you can even create graphs that are not fully connected. But on the other hand, if you connect to too many neighbors, you can create these short circuits. So that if you have on the Swiss roll a point that happens to be sort of off the manifold, you can sort of connect them, and this will distort the whole structure of the manifold. So it's very important to choose the neighborhood size. But this area on the mapped key points on the geographical coordinate system gives you an area measure independent of the manifold in a way, and you can use this to choose the neighborhood size. So that's very useful because it's really a crucial point in making the ISOmap work properly. And again, so here's now we've got the floor plan. Here, as I said, we had 2 rooms where we couldn't enter or didn't want to enter actually. There's an open space here where the points tend to cluster because there's no really change in the signal variation, signal strength here. So the points are hard to separate. But along the corridors, it's easier because the signals clearly change when you walk along the corridor. Some of the points tend to sort of move in or through the walls, which you could actually somehow try to correct for. But there are ideas on how that could be done. But this is really the same data. So you have this rectangle here, and there's a corridor in between, which we could also see in the data. And the data that we used was 440 almost points, of which 38 were labeled. So less than 10% were labeled instances. And we got, the average error was 2 meters. So that's should be useful for many purposes. Finding the toilet, for instance. Yes?
Isn't there some additional information that you could use, which is basically the time of measurement?
Right, they should be close to one another.
Move smoothly through your space,
right.
And that would tell you which points are in fact neighbors on that trajectory on which you were moving, which might reduce some of the ambiguities in the manifold learning.
Yes, yeah, that's a very good point, but it's not very clear how you could incorporate that and still maintain the sort of computational feasibility of the system. Right now it's very, very simple to use and apply, but yes, those things could be taken into account, that these points are actually neighbors, since you know that there was only 1 second between them or something like that. And as I said, the walls could be somehow exploited to know that you don't walk through walls, for instance, that often. Okay, so I guess that's pretty much it. It's very simple how it works, and seems to work pretty fine. So that's basically all that I had to say for now. There are consequences of this. So some people find this creepy that you could locate them, but I don't know how you feel about that. Yeah, that's all. Thanks.
All right, thank you.